the difference between, I guess, 2-unit and 3-unit. In 2-unit, every motion problem, it's with respect to time. And that's pretty much all they do. But there's no reason why a formula has to be with respect to time. It is possible to write velocity and acceleration equations in terms of its displacement rather than in terms of time. So we take time out of the equation. I guess a bit like in projectile motion when we made it the Cartesian equation. We took time out of it, although that was linking two displacements together. So a little bit different. So if velocity is some function of x, then what we know is this: the acceleration is equal to, it's still the derivative, but be very careful. We don't just differentiate velocity to get acceleration now. That only works if it's with respect to time. If velocity is with respect to displacement, then what we differentiate is actually a half v squared. A half v squared. Now, let's show you why that works. So what we do know is acceleration is the derivative of velocity with respect to time. I could rewrite that right-hand side as using the idea of the chain rule, implicit differentiation, whatever you want to call it. So dv dx times dx to t. Well, dx to t is velocity. That step there also becomes very important because that's another way we can write acceleration. V times dv dx. When we're dealing with some of these problems, you'll see me using that actually rather than the d dx of a half v squared. But v times dv dx. But anyway, let's get to what we're trying to prove. Velocity I can rewrite as the derivative of a half v squared with respect to v. And if you differentiate a half v squared, you would get v. But now the dv's cancel, and there's our formula, d dx of a half v squared. So acceleration can be written as d dx of a half v squared. So here's a question. A particle moves in a straight line, but they've given us acceleration in terms of displacement rather than in terms of time. So we want to find its velocity in terms of displacement. Okay. So d dx of a half v squared, that's acceleration. If I integrate both sides, so d dx of a half v squared will become a half v squared, and the right hand side 3x minus x squared plus c, I now have velocity in terms of displacement. Well, okay, I've got velocity squared in terms of displacement, but I can easily get to velocity from that. I've got to work out that constant, of course. Some initial conditions: when v equals 2, x is 1. Sub that in. Conveniently for this question, the constant turned out to be 0. So all right, v squared, I've just multiplied both sides by 2 there. So v squared is 6x minus 2x squared. That's not the question though. It was not to find v squared, it was to find velocity. So velocity is plus or minus. And you might be thinking, hang on a sec, how can an object have two velocities? But remember, we've taken time out of this. So it can be at a particular point at two different times. And so one time it might have a velocity of positive the square root. So one time it might be moving to the right, but another time it might be moving to the left. So it is possible to have two velocities. We're just talking about two different times. So velocity is plus or minus the square root of 6x minus 2x squared. Now, personally, these are the ones I prefer to do definite integrals with. And if I do definite integrals, instead of using d dx of a half v squared, I'll use that step v to v dx. Because then I can separate the variables. I've got everything with respect to v on the left-hand side, everything with respect to x on the right-hand side. Match up the conditions. We said, well, when x is 1, velocity was 2. So I put that on the bottom of my integral. And then on the top I'm saying, hey, I want a relationship between v and x. Now, you'll see why I use the v to v dx when I integrate, because, of course, integrate v with respect to v, you get a half v squared. So you're back to the d dx of a half v squared. So it's easier to write it as v to v dx rather than try to say, oh, I want the integral of d dx of a half v squared with respect to, and I'm starting to mix up my pronumerals. So if I use v to v dx, I can separate the pronumerals quite easily there. All right, let's sub in, and it works out the constant for me. We've got -2 on both sides, so they cancel, and there's that constant of 0 that we got. So v squared is 6x minus 2x squared. What this allows me to do now is to actually investigate the particle a little bit, because one of the things we know is v squared has to be greater than or equal to 0. Or another way of thinking of that is, the square root has to be positive. Either way, what we're saying for this one is 6x minus 2x squared is greater than 0. Solve that inequality, and we find out where our particle is travelling. It only goes between 0 and 3 and nowhere else. Poor little particle. It hasn't got much fun really when you think about it. It's between 0 and 3. So I can use that to find out the path of the particle. Let's have a look at another one. Acceleration this time 3x squared. Again, they've given me some conditions and so on. But now they're saying, hey, I've given you acceleration in terms of displacement. Can you get right back and get that displacement in terms of time and bring time back into it? How do we do that? Okay. Well, they've given me acceleration in terms of displacement, so d dx of a half v squared. I'll integrate half v squared, in this case will be x cubed plus a constant. I'm looking for conditions that link velocity and displacement together, and we've got initially the particle 1 unit to the right, so I know initially when t equals 0, well, there's nowhere to substitute t in, but x equals 1 and v is -√2. So I can sub in the x and the v. Oh, again, how convenient. The constant was 0. Look, don't assume the constant's always going to end up being 0, okay? So it's a little equation, v squared equals 2x cubed. So again, velocity is plus or minus the square root of 2x cubed. If I did it as a definite integral, then I'd start with v to v dx. I'd separate my variables. Again, I'm matching up those limits to the initial condition. When x equals 1, v is -√2. Integrate both sides, substitute in, and I come up with the same answer. v squared is 2x cubed. Okay. I now have velocity in terms of x, but velocity is dx to t. So this is how I'm going to now find an equation for displacement with respect to time, because I could integrate this. But you'll notice I haven't said plus or minus. Okay? Because when I perform the calculus on it, I have to perform it on a function. And of course, functions only have one possible value, not two. So why did I choose negative rather than the positive? And it all comes back to the initial conditions that I'm using. The answer has to be correct. If I'm going to use the conditions t equals 0, x equals 1, v equals -√2, then when I substitute into here x equals 1, I have to get the answer v equals the negative square root of 2. Because they're the conditions I'm going to use. So I need to take the negative square root, not the positive square root. Now, yes, it'll be the positive square root, possibly at another time, but I'm not using that other time. I'm using t equals 0. And at t equals 0, it only has one velocity, and that's the negative square root. So that's why I'm using the negative one. So basically, we've got to satisfy the initial conditions or whatever conditions we're using to solve the problem. Okay, well that's dx to t. Oh yes, I'm going to need that in index form. But I'm going to turn it upside down because I need it with respect to x. So I turn it upside down, I'll get the t dx. That's -1 on √2, x to the -3 on 2. Okay, add 1 to the power over the power, plus some constant. I'll work out the constants a little bit later, but playing around with that expression, 1 on root 2 times 2 becomes root 2. X to the minus a half is on the bottom of the fraction, square root of x. I end up with this root 2 over x plus some constant. All right, now let's work out that constant. When t equals 0, x equals 1, and finally the constant's not 0. In this case, the constant is the negative square root of 2. What an ugly looking answer. So t equals the square root of 2 on x minus the square root of 2. Of course, if I did that as a definite integral, then the dt dx, I'll separate the variables. This time the linking information on the bottom of the integral there was that when t equals 0, displacement was 1. I'll integrate. Whenever you've got a definite integral, which is just going 0 to something to t, we usually just jump straight to t. Because if you think about it, integrate the t, you're going to get t. Substitute in t, substitute in 0, you'll just be left with whatever's on top there. On the right hand side, I've got my definite integral, and well, that equates to be the same. If I expanded that, you'd see it would. But now let's play around with it, because that's not the final answer. They didn't ask for an expression for time in terms of displacement. They asked for displacement in terms of time. Probably one of the biggest mistakes I see with questions like this is people stop there and go, yes, I've done it. But that's not what the question asked for. So, all right, we need to make x the subject. Move the square root of 2 to the other side. Trying to isolate the x. Square both sides. Turn both sides upside down. Then multiply by 2. And we've got the beautiful expression there for displacement. T over the square root of t plus root 2 all squared. So let's have a look at this HSC question. Nice and conveniently, we're moving along the x-axis, or our particle is. They've given us some initial conditions, told us the initial velocity as well, and we have acceleration in terms of displacement. They were very nice to us. They've actually told us the answer we should end up getting. So we want to get to velocity. Okay. d dx of half v squared is acceleration. So I'll substitute that in for acceleration. Integrate both sides. Now let's work out the constant. They told me when x equals 2, v was 5. Sub in, our constant is a half. I think I'm going to multiply everything by 2 there. Yeah. So v squared is x to the 4 plus 2x squared plus 1. So we're not quite there yet. Now, before I move on from there, let's have a look at the definite integral way of doing it. So now I would use v to v dx, separate my variables, match up the conditions there. So when x is 2, velocity is 5. Integrate both sides. Now, notice what I did here. Instead of writing a half v squared on the left-hand side when I integrated, I multiplied the other side by 2. Because I know eventually I'm going to do that anyway. So, I'll just do it there. Substitute in and move some terms around and we get the same thing. So, okay, we've got v squared. We need to get to x dot is x squared plus 1. Well, x dot is, of course, velocity. Well, if you actually have a look at the right-hand side, that is a perfect square. So v squared is x squared plus 1 squared. So velocity is x squared plus 1. And people would do that and they would be happy and they wouldn't get full marks. Because the question is, hang on, no. Velocity is plus or minus x squared plus 1. Why did you choose x squared plus 1? Can't it be negative? So that's where you need to explain why you chose the positive. Well, I know velocity is greater than 0 in order to satisfy those initial conditions. And in fact, when you look at our velocity, because we've now chosen it, and it turns out to be x squared plus 1, it will never be negative. because I'm starting at x equals 2. So I'll start with a velocity of 5, which means I'm going to move in the positive direction. My x is going to get bigger and bigger and bigger. So velocity is going to get bigger and bigger and bigger. It's never going to stop. So actually, in this case, this particular particle will never stop and go back. It'll always just be travelling to the right. Okay, now we're going to find an expression for x in terms of t. So we have our velocity, but we'll now call it dx to t. And I'm just going to go straight to the definite one because I just think it's easier. So I've separated my variables. Now be careful with that one. Remember the dx, so the x squared plus 1 is going on the bottom of the fraction there. Integrate from 0 to t, that's easy. Right hand side, inverse trig we've got. It's going to be an inverse tan function. So on the right hand side we've got inverse tan of x going from 2 to x. So there's t in terms of x. We want x in terms of t. So let's rearrange it. Inverse tan of x is t plus the inverse tan of 2. To undo the inverse tan, I'll tan the other side. There's an answer. Yeah, it's a mere mortal answer, but it's an answer. X in terms of t. But look, I've got a tan of alpha plus beta. I can go tan plus tan on 1 minus tan. And that looks much nicer. Because I'll go tan of t plus tan of the inverse tan of 2. Well, that'll just be 2 over 1 minus the tan. I'd say that second last step, well, it is an answer. So, but it's just, I can impress people with. Okay. So exercise 3, we'll add that to our list of questions, looking at this idea of velocity and acceleration in terms of displacement.